heat transfer and entropy change. What is the relation between heat transfer and changes in the entropy of a system? Let us write down the first law in the form that delta Q plus delta W is equal to du. For a reversible compression or expansion process, we know that the work done, delta W, equals minus P dV. Substituting this back into our first law, we have that delta Q is equal to du plus P dV. For an internally reversible process, therefore, delta Q is equal to du plus P dV. Next, let's write down the Gibbs equation. ds is equal to 1 upon T du plus P upon T dV. Taking 1 upon T common, we have 1 upon T into du plus P dV. But this, we have shown, is equal to delta Q. We can therefore write ds is equal to delta Q over T, and we put the subscript internally reversible to remind ourselves that we have assumed that this is an internally reversible process. If we take this equation and we multiply both sides by the system mass, then on the left-hand side we have ds, where capital S is the total entropy of the system, and on the right-hand side we have delta Q, where capital Q is the total heat transfer to the system. The change in entropy, delta S, then is the integral of delta Q over T. For a thermal reservoir, the temperature T is constant, so delta S is equal to Q12 divided by T, where Q12 is the total heat added to the system in taking it from state 1 to state 2. On a rate basis, we can write that ds by dt, which is the rate of change of entropy of the system, is equal to Q dot divided by T, where Q dot is the rate of heat transfer. For an irreversible process, we can write that the change in entropy, delta S, equals the integral of delta Q upon T plus S gen. The integral of delta Q upon T is the entropy change with heat transfer. S gen represents the entropy generated. Since entropy can only be generated, not destroyed, S gen must be greater than 0. Delta S, therefore, is greater than the integral of delta Q upon T for an irreversible process. A rigid container is filled with gas, which is at some temperature T1 and has entropy S1. We can represent a heating process on a TS diagram. So we mark the initial state at T1, S1. The gas is now heated until it reaches a final state with temperature T2, entropy S2. We can mark that state also on the TS diagram. The process is then shown by this line joining state 1 to state 2. If we use the equality that ds is equal to delta Q upon T for an internally reversible process, we can rewrite that to say delta Q is equal to TdS. The heat transfer, therefore, Q12 would be the integral of TdS from state 1 to state 2. This integral represents the area under the process curve. The area under TS curve therefore gives the heat added for a reversible process. An isentropic process can also be represented on a TS diagram. Here we have gas which is contained in a cylinder and it is being compressed by a piston. We insulate the cylinder so that this is an adiabatic process. The gas is then compressed in a reversible process. Since this process was adiabatic and it was reversible, we know that that is an isentropic process. So the entropy remains constant and S1 is equal to S2. On a TS diagram, that would be represented by a vertical line where it goes from T1 to T2, but S1 remains equal to S2. A reversible process then looks like this on a TS diagram. So it's going from state 1, where the temperature is T1, and it goes to state 2S, and we add an S to remind ourselves that this is a reversible process. At that final state, the temperature is T2. Now, if we had done the same compression, but in an irreversible process, so that there was entropy generated, then the entropy of the system would have increased. If we now represent that process on the same TS diagram, then the final state would be 2, where the temperature would still be T2, but the entropy now would have increased to a value of S2. This dashed line therefore represents an irreversible process. To summarize, for a reversible process, the change in entropy, delta S, is the integral of delta Q upon T. For an irreversible process, delta S is equal to the integral of delta Q upon T plus the entropy generated, Sgen. Heat transfer processes can be shown on a TS diagram, and the area under a TS curve gives the heat added during the process.